Lemon for this great introduction, and I'd also like to take a chance to thank GEM community to give me this chance for the plenary talk. My topic would be about system understanding of radiation belt particle dynamics through multi-spacecraft and ground-based observations and modeling. And this is also the topic of our new focus group this year. So I would also like to thank our co-chairs, Lauren Blum, Sasha Yudkowsky, and Xiang Fu, and also thank the Violent Probe Science and Instrument teams and the GEM community for your support. So this is the outline of my talk today. Since Wen Li has given a very comprehensive tutorial done smartly about radiation belt waves, in this talk I will mainly focusing on the radiation belt particle dynamics. So first, we'll do some introduction of radiation belt particle dynamics, and then we'll focus on some recent advances in radiation belt studies based on the violent probe measurements. Then we'll switch gear to the system understanding of radiation belt particle dynamics through multi-spacecraft and ground-based observations and modeling. The last part would be a summary. So Earth's magnetosphere is a tear-shaped region carved out of the solar wind by Earth's magnetic field. While close to the Earth, there's the Earth's inner magnetosphere, which is a region that geomagnetic field resembles a dipole field. It includes the several parts of plasma sphere, radiation belts, and ring current. While charged particles and ring current systems existing in the inner magnetosphere can pose potential threats to the spacecraft and human in space, as well as some technical systems on the ground. So it is very important for us to understand their behavior. Charged particles in geomagnetic field exhibit three different kinds of motions. They gyrate around the magnetic field line, bounce between the two middle points along the magnetic field line, and drift around the Earth. The time scales of three different motions are very distinctive. Another two important parameters we often use in radiation belt study is L shell and pitch angle. So L is approximately can be seen as the geocentric distance in Earth's radii from the center of the Earth to the location where the geomagnetic field line intersects the geomagnetic equator. While the pitch angle of a particle is defined as the angle between the particle's moving direction and the local magnetic field direction. So corresponds to three different motions, we have three adiabatic invariants. The first adiabatic invariant, mu, corresponds to gyration. Second adiabatic invariant, sometimes we use J, sometimes we use K, corresponds to the bounce motion. And third adiabatic invariant, mostly we use L star, corresponds to drift motion. So we have these three adiabatic invariants, then we can constitute a phase average phase space coordinates, which is mu, K, and L star. And then we can calculate the phase space density by using the flux measurements divided by the particle's momentum squared. So those adiabatic invariants usually conserve if the magnetic electric field fluctuation is very slow. However, if the time scale of this field fluctuation is shorter compared to the particle's motion period, these adiabatic invariants can be violated. And the violation of the adiabatic invariants causes diffusion processes. So diffusion process is a process that moves particles from high concentration region to low concentration region. There are several forms. The radial diffusion, which permits the transport of particles across the field lines. Pitch angle diffusion, which alters the particle's pitch angle, and energy diffusion, which changes the particle's energy. As we'll also discuss in her tutorial Monday, magnetospheric waves can cause diffusion processes, and there are a zoo of magnetosonic waves in the inner magnetosphere, so I'm not going to touch very detail about this part. Then let's focus on the Earth's radiation belts. So the radiation belts are the torus-shaped regions consist mainly of energetic electrons and protons geomagnetically trapped and azimutally drifting around the Earth. The radiation belts consist of outer radiation belt, which generally located at L about 3 to 6, consists of energetic electrons with energy from about tens of keV all the way to tens of MeV. And the inner radiation belt, which located at L about 1 to 2, mainly consists of very energetic protons and some of tens to hundreds of keV electrons. The region in between, which is called slung region, is usually devoid of energetic particles, but during very active times, it can also be filled with energetic electrons. The major source processes for radiation belt electrons have been proposed as the inward diffusion and local acceleration. This schematic from Reeves et al. In 2013 shows the phase space density radial profile to be influenced by the inward radial diffusion and the local acceleration. So if the inward radial diffusion is the main acceleration mechanism, we would expect such kind of positive radial gradient in the phase space density radial profile because we have a source at high L star region. If the local acceleration by waves is the main acceleration mechanism, we would expect a locally growing phase space density peak at some L star, since waves are usually localized. Well, the major loss processes for radiation-bound electrons, including the magnetopause shadowing, where the particles drift to magnetopause and lost, precipitation into the atmosphere, which one has covered in her talk a lot, and outward radial diffusion, which can bring particles outward and get de-energized. So since the launch of Explorer 1 in 1958, we start to have measurements of radiation-bound particles. And prior to the Van probe era, we have several missions provide long-term variation of radiation-bound electrons. Here are just two examples. The left figure is using the CREST data for different energy channels from about 100 keV all the way to 1.5 MeV electrons. As we can see, the CREST data provide measurements of these differential energy channels of radiation-bound electrons for over a year or so. And we can clearly see the radiation-bound electrons are very dynamic and they exhibit energy-dependent behaviors. The right figure here shows the 226 MeV electron fluxes measured by SAMPEX satellite, which is a low Earth orbit satellite and lasts much longer. We can see over 10 years time period, there's a very significant variation of these multi-MeV electrons in the outer radiation belt. And their variation seems well correlated with the solar wind parameters. So that suggests that radiation-bound particles are subject to significant influence from the solar wind. Even though we have observations of radiation-bound particles long before 60 years ago, but Van probes still provide us the most comprehensive measurements of radiation-bound particles and waves. So launched on August 2012, the Van probes are twin probes that operating in an elliptical plane close to the geomagnetic equator. They provide the comprehensive measurements of radiation-bound particles from tens of keV all the way to tens of MeV, and it's ideal for our radiation-bound studies. So a lot of progress has been made using the Van probes data, and I don't have time to go through all of them, so I'll just show some highlights. This left figure here from Fennell et al. In 2015 showed background-corrected MAGIS data for different energy channels of radiation-bound electrons. And they found that for hundreds of keV electrons, you can see there's abundant, there's abundant hundreds of keV electrons in the inner belt. However, as energy gets higher, there are very limited MeV electrons in the inner belt. Most recently, Claude et al. In 2019, using a new background removal algorithm to reprocess the MAGIS electron background removed flux data. And they found that indeed, for tens of keV all the way up to several hundred or even MeV, we can still see quite abundant electrons in the inner belt. However, we note that during the whole Van probe era, there are only very few injections of MeV electrons down to low L region. And specifically, there are very limited multi-MeV electrons in the low L region. The right figure here from Baker et al. In 2013 showed the rapid measurements on board the Van probes from the very beginning of the mission, first months of the observations. This flux plot is for 4.5 MeV electrons, and red plot shows the different solar wind parameters and DST indices. They found that based on the first month's data, there's a very clear new gray belt structure where we can clearly see there's a double outer belt. Such kind of structure is believed to be formed as the fluctuating plasma pulse, as well as the local acceleration outside the plasma pulse and loss inside the plasma pulse. Also, Baker et al. In 2014 studied the longer-term behavior of these multi-MeV electrons and found that there is an impenetrable barrier for those multi-MeV electrons, which located generally at L about 2.8 or so. And those multi-MeV electrons seems cannot penetrate through this barrier to low L region during the Van probe era. So Van probe measurements also revealed some L and energy-dependent features of radiation belt electrons. The left figure here from The left figure here from Reeves et al. In 2016 showed the energy L distribution of the radiation belt of electrons with a whole range of energy and L shell. They showed that there is an S-shaped structure in energy L distribution during these quiet times, which suggests there's an energy-dependent location of the slot region. However, during active times, because of the injection into the slot region, such S-shaped structure just disappeared. And further, Ripple et al. In 2016, through a modeling, confirmed that S-shaped structure is actually formed as a result of plasma-spheric Higgs-wave scattering. Well, Van probe observations also provide us a great opportunity to look back into the radiation belt electron energy spectrum. So since the discovery of the radiation belt, the energy spectrum of radiation belt electrons is always thought to be steep falling with energy, which means there are fewer high-energy electrons and more low-energy electrons. However, using the Van probe data, we show that sometimes there's a reverse energy spectrum in the energy range of hundreds of keV to 2 MeV. Just as here, our observations show, between L at 3 and 4, after a significant storm, we see a faster decrease of hundreds of keV electrons, while for MeV electrons, their fluxes almost do not change, which finally formed a reverse energy spectrum in this range. And for this energy spectrum, we call it Bonpang-Tiao here. Through a more statistical analysis, we found that this Bonpang-Tiao energy spectrum is actually the most prevalent energy spectrum inside the plasma sphere at L greater than 2.6 also. We also did a simulation using a two-dimensional Fokker-Coulomb equation with a data-driven time-varying Higgs-wave model, and we well reproduce our observations of the formation of this Bonpang-Tiao energy spectrum. These results suggest that plasma-spheric Higgs-wave scattering is actually responsible for the formation of such a Bonpang-Tiao energy spectrum inside the plasma sphere. So the effect of solar wind on the radiation belt particles have been examined over a long time. However, the state-of-art measurements from Van probes enable us to further understanding the effects of solar wind on radiation belt electrons, especially with their energy dependent. So here I'll just show two examples of the most recently published paper. The left figure here is from Baker et al. In 2019. They showed 6-year rapid measurements of different energy electrons from 1.8 MeV all the way up to 6.3 MeV. And we can see there's clearly energy-dependent behavior exists in this long-term variation of these multi-MeV electrons. They also showed during the same time period the solar wind speed, and also it suggests that whenever the solar wind speed exceeded 500 km per second, we would expect some kind of flux enhancement in the multi-MeV electron flux in the outer belt. Well, another companion paper we published early this year also, we separated the events to the enhancement events and non-enhancement events for the multi-MeV electrons and performed the superposed epoch analysis of solar wind parameters during these events respectively. Here, the red lines are results for the enhancement events, and black lines are results for non-enhancement events. Well, we can see across these different solar wind parameters, the biggest difference exists in the solar wind speed, which is much higher during the enhancement events compared to the non-enhancement events. And even though I did not show here, these differences are even larger when we go to the higher energy electron enhancement events. So this study suggests that solar wind speed is the most influential solar wind parameter that's affecting multi-MeV electron flux enhancement. So Van probe also provides deep insights into the acceleration of radiation belt electrons. The left figure here from Reeves et al. In 2013 studied the phase space density evolution during an intense storm of October 2012. And as shown in this figure, you can clearly see there's a locally growing phase space density peak at the outer belt, which suggests that local acceleration is the main acceleration mechanism responsible for accelerating those particles. Further, Stone et al. In 2013, using a two-dimensional model and data-driven global Chorus wave model, well reproduced the results during the same event. They show that by using Chorus wave acceleration only, they can well reproduce a 2 to 7 MeV electron flux enhancement in the outer belt during this event. So both studies suggest that local acceleration is a very important acceleration mechanism for these multi-MeV electrons during this storm. However, we also have other studies using one probe data showed that inward radio diffusion is also a very important acceleration mechanism for radiation belt electrons. The left figure here from Li et al. In 2016 studied an intense storm of March 2015 and compared the results of observations with their modeling results. So in their model, first they only include the radio diffusion and then only include coarse wave acceleration and the last combine the two. By comparing all these different results, they found that both coarse wave acceleration and inward radio diffusion contributes to the flux enhancement during this storm. Especially for multi-MeV electrons, the inward radio diffusion could become a dominant role. For Jens et al. In 2018 also studied a specific event focusing on the fast inward radio diffusion of multi-MeV electrons. So here the flux plot is for 6.3 MeV electrons. You can see a very clear fast inward radio diffusion processes occur during this time, suggesting that inward radio diffusion could be a very important acceleration mechanism for multi-MeV electrons. Similarly, we published a paper last year focusing on the evolution of phase space density during a small to moderate storm. As you can see here, for 8,000 MeV per G electrons, which corresponds to about 3.5 MeV at L star about 4.5, we can clearly see a growing local phase space density peak during this small to moderate storm. This suggests that during this time, local acceleration is the most influential acceleration mechanism for these particles. However, as we go to even higher energies, 16,000 MeV per G electrons, which corresponds to 7 MeV at the center of outer belt, we can see, as the Van Hoek's measurements show, the phase space density radio gradient is almost always positive during this small to moderate storm, suggests that in this outer radiation belt region, the inward radio diffusion is actually the main acceleration mechanism for such kind of very high energy electrons. So yeah, I've talked about some studies with recent advances using Van probes observations. However, note that although Van probes have helped us greatly advance our understanding of radiation belt particle dynamics, we still have some open questions remain which need to be fully answered. For example, how about the quantification of different source and loss processes on radiation belt electrons? To answer these questions, there are multiple ways, but just to mention that we often have this limitation in single-point measurements, which have spatial temporal ambiguities and limited coverage. But now we are in an era of heliophysics system observatory, which means we have a lot of measurements from different satellites, different missions, at different orbits. So through coordinated measurements from those multi-spacecraft and ground-based observations, combining with theoretical and modeling efforts, we can gain further advanced understanding of radiation belt particle dynamics. I'll just show some examples of how multi-point measurements help us to further understand the radiation belt particle dynamics. So this study conducted by Boyd and al. In 2018 studied the evolution of phase space density during enhancement events of radiation belt electrons. They showed that when the Van probe data only was used, it's about 30% of enhancement events show clear local acceleration dominant feature, which is locally growing phase space density peak. However, if we combine data from Van probes and SEMIS, which have a coverage over a higher L region, we can see the majority of those events are actually dominated by the local acceleration caused by coarse waves. Multi-point measurements can also provide global pictures of substorm injection, which provide very important source and seed populations for radiation belt electrons. This study by Turner et al. In 2017, using data from over 10 satellites of energetic particle measurements, detailed studied the substorm injection evolution and the spatial temporal distribution of several injections during a specific event. So such kind of multi-point measurements provide very comprehensive information of spatial temporal evolution of such injections and will be very important for our radiation belt study. Multi-point measurements also can provide important information of electron precipitation. This study, conducted by Blum et al. In 2013, used the data from CSSWE, which is a low Earth orbit CubeSat, and the Barrel, which is a balloon measuring precipitating electrons. They showed that both CSSWE and Barrel observed the same precipitation band signature of radiation belt electrons during a single event. And using data from both missions, we can confine the precipitation region into a more confined IL and MLT ranges. And the electron precipitation can thus be better quantified. On the other hand, multi-point measurements also provide better understanding of radiation belt wave properties. So here is just two examples. So the first one is conducted by Gapitov et al. In 2017. They're using conjunctive measurements from the 2-1 probes, conduct a statistical analysis on the spatial and temporal scales of quartz waves. And the right figure similarly is from Blum et al. In 2017. They also use the conjunctive measurements to study the spatial and temporal evolution and scale of IMAG waves. So such kind of detailed information on radiation belt waves would help us better to understand the wave distribution and properties, and in turn would better understand the wave particle interaction and their effect of radiation belt particles. So that would be my talk today, and here is a brief summary. Radiation belt particles generally exhibit significant variations under the effects of various source and loss mechanisms, while recent advances have been achieved on understanding the radiation belt particle dynamics because of the unprecedented measurements of the Banner probes. However, we can foresee now that coordinated multi-spacecraft and ground-based measurements, combined with theoretical and modeling efforts, will further deepen our understanding of radiation belt particle dynamics. And this is also the main goal of our new focus group. Thank you.